Have you ever actually stopped to think about what it takes to get clean, safe water from your tap? It's this incredible, complex journey, all the way from a river or a reservoir straight to your glass. Well, in this explainer, we're going to break down every single step of that process, covering exactly what you need to know about treating contaminated water. Let's get into it.
So, to really get why this all matters, let's just look at the bigger picture for a second. This quote from the UN is pretty staggering, isn't it? The huge majority of water we use is just flowing straight back out there, totally untreated. And that's exactly why understanding these processes isn't just, for an exam. It's absolutely vital for our health and for the future of the planet.
So here's our game plan for this journey. First up, we'll look at the problem itself. What kind of contaminants are we actually dealing with? Then we'll follow the water through each stage, starting with simple physical removal, moving on to some clever chemistry, and then the final polish, sterilization. We'll also look at the special case of desalination before we wrap it all up.
Right then, first things first, before you can even think about treating water, you've got to know exactly what you're up against. So what are the things we actually need to get rid of? Okay, this is basically our hit list. We're talking about everything from the really obvious stuff like litter down to tiny bits floating in the water, what we call suspended solids like silt and clay. Then you've got the invisible threats, dissolved metals, organic pollutants like pesticides, and of course, salt. And finally, the really important one for our health, pathogens. Those are the nasty little microorganisms that cause disease. As we're about to see, each one of these needs its own special removal plan.
Let's kick things off with the most straightforward part. This is all about getting rid of the stuff you can actually see, using physical methods rather than complicated chemistry.
The very first line of defense is called screening. Honestly, just think of it like a giant sieve. As the water flows into the treatment plant, it passes through these big metal grills that catch all the large rubbish, plastic bottles, leaves, bits of paper. It's so important to get this stuff out early, so it doesn't end up damaging or clogging all the equipment further down the line.
Once all that big litter is gone, we need to deal with the next level of solids. The water is moved into these huge, still tanks, and here we just let gravity do all the work. Heavier particles like sand and silt just can't stay floating, so they slowly settle down to the bottom. This forms a layer of sludge that can then be scraped away. It's simple, but it's really effective.
But sedimentation has a bit of a weakness. It doesn't really work for super fine particles, like clay. They're just so small and light that they stay suspended in the water. And the reason why is actually pretty cool. They all have tiny electrical charges on their surfaces, which makes them repel each other, so they just can't clump together and sink.
So how on earth do we get these tiny particles to sink? Well, we need a bit of chemical magic. We add something called a flocculant. The most common one is aluminum sulfate, which is usually just called alum. Its whole job is to take care of those annoying repelling charges.
And here's how it works. When you mix the alum into the water, it gets to work neutralizing those pesky electrical charges on the clay particles. This means they stop pushing each other away, and now they can finally stick together, forming bigger, heavier clumps called flocks. These flocks are now dense enough to sink to the bottom, leaving the water much clearer. And that whole process is what we call clarification.
Okay, so we've handled all the solids we can see. But what about the threats that we can't see? Now we have to start tackling all the things that are actually dissolved in the water. This is where we get a bit more technical. For things like weird smells or some dissolved metals, the solution is surprisingly simple: aeration. You literally just bubble air through the water. This can get rid of odors, and it makes some metals turn solid so they can be filtered out. For more difficult organic pollutants like pesticides, we use activated carbon filters. Think of it like a chemical magnet. The carbon has a massive surface area, and the pollutants just stick right to it. That's a process called adsorption. And finally, to get rid of really toxic metal ions like lead or mercury, we use something called ion exchange, where the water flows through special beads that trap them.
We've gotten rid of the solids, and we've dealt with the dissolved chemicals, but the water could still be hiding dangerous, invisible life. And that brings us to what is probably the most critical step for our health: sterilization.
So what's this all about? Well, sterilization is all about destroying pathogens. These are the bacteria and other microorganisms that, if we didn't get rid of them, could make us seriously ill. This is the final safety gate. This is what makes water truly safe to drink.
Now, the most common way to do this is with chlorine. Adding a small, controlled dose of chlorine is great because it doesn't just kill the pathogens at the treatment plant, it also provides what's called a residual effect, which keeps the water safe all the way through the pipes to your home. But there is a catch. If the water has come from a peaty area with lots of organic stuff in it, chlorine can react with it and create some nasty byproducts. In those situations, we use alternatives like ozone or UV light. They're great at killing germs, but their effect doesn't last as long once the water's in the pipe network.
Okay, now for something a little bit different. Everything we've talked about so far is for freshwater sources like rivers. But what happens if your main source of water is the ocean? Well, that requires a completely different process: desalination.
Desalination is exactly what it sounds like. It's the process of removing salt from seawater. For lots of dry countries where fresh water is hard to come by, this is an absolute lifeline. The big challenge, though, is that it takes a massive amount of energy, which means the fresh water you get at the end is really expensive.
The main method we use today is called reverse osmosis. What happens here is that saline water is forced at incredibly high pressure against a special membrane. This membrane is pretty clever. It's partially permeable, which means it lets the tiny water molecules squeeze through, but it blocks the bigger salty ions. So what you get is pure, fresh water on one side and all the concentrated, salty stuff left behind on the other.
The more traditional way of doing it is distillation. You've probably done this in a science lab. You just boil the seawater. The water turns into steam, leaving all the salt behind, and then you just collect and condense that steam back into pure liquid water. It works perfectly. But can you just imagine the colossal amount of energy it takes to boil that much water? It makes it even more expensive than reverse osmosis for doing it on a large scale.
And there we have it. We've followed the water right through every stage of its purification journey. So let's do a quick-fire recap just to bring it all together.
So let's run through it one more time. Litter gets taken out by screening. Suspended solids, that's sedimentation and flocculation. Metals and odors are removed with aeration. Organic pollutants are dealt with by activated carbon. Pathogens are zapped by sterilization. And finally, salt is removed by desalination. There really is a specific solution for every single type of contaminant.
So we've seen the incredible science and engineering that goes into every single glass of clean water. But it does leave us with a really important question for the future. You see, a lot of these processes, especially desalination, are incredibly energy hungry. As our climate changes and our populations grow, putting more and more stress on our freshwater supplies, the real challenge is this: how can we innovate to make this essential journey from contaminant to tap not just effective, but truly sustainable?